In the name of the Lord, falling weight deflectometer or FWD is not reliable for pavement evaluation. Roads are the wealth of any nation, and there is no question on the necessity of the procedure of maintenance. FWD is widely used for evaluation of the procedure of for for pavement evaluation in the procedure of maintenance in the United States. In my thesis, I want to prove that the FWD method can be misleading, and at its best, it is a redundant procedure in pavement evaluation. The claim critics on my thesis was on its language, and this is why I write and record the presentation to avoid any accidental error in speech or misunderstanding. It takes a bit longer than the general defenses, and I appreciate your patience. Slides 32 to 39 are the main arguments of the thesis. The rest is the preparation to prove the hypothesis that since now there were no conflicts on it, uh, I will try my best to simplify my presentation for general authorities. Have you ever tried to heat the watermelon to qualify it without taking a slice of it? The idea is the same. We drop a weight on the pavement and we record its response at several distances. As you can see, this is the area of the load, this blue circle, and in the center of that we have a sensor which measure for us the central deflection, and at 8 inch, at 12 inch, and so on. Uh, with the hope that we can evaluate the condition of pavement by recording its response. So here is the central deflection, exactly under the load, the maximum central deflection along the 2 kilometer of the NC96 that I normalize it for 9 kips. So general FWD test on the regular pavements is 9 kips, and but sometimes it is in action it becomes 8.9 kips, or it becomes 9.1 kips. So I just took the ratio of that and normalize it for 9 kips. We have 2 consecutive drops, and it shows us that at single location, if we repeat the drop, it does not change much the response. And we did it for the same design structure, so we did not use for example, the intersections that its designs is as it has a thicker AC layer. So as you can see, almost every 24-meter distance that we tested, we had significant jump. For other sensors, it was not also, the condition was not better. Or each point of the watermelon has its own specific voice. What is the reason? Can we translate these point-wise deflections into some other quantities, such as a modulus of asphalt concrete or AC layer, which can be used for pavement evaluation? This idea that we change these deflections to some physical quantities, the properties of pavement, it is called back calculation. But why it is called back calculation? It is because it is somehow backward. If we know the properties of pavement, so most probably we are able to model that in computer and then apply the load on that and then see what is the response of that. But if we know the response, it is backward. So we want to know what is inside the pavement. It is so we should do it by trial and error. So first we begin with an estimate, then we compute the displacement through forward model, and then we compare the measure displacement on the field with the forward model, and the difference we call it misfit. And then if the misfit was less than tolerance, and we didn't face the problem of non-uniqueness, we assume that we find properties. But if it was more than tolerance, we cannot say that we found, and we should go to the next trial and we again estimate the properties, and this loop is to be continued until we find the properties. This is called the procedure of back calculation or inverse problem inversion. As you can see, the forward model is a very essential part of that. If we cannot make a forward model, we cannot use this type of back calculation. There are unavoidable assumptions that all the programs in the literature they consider as such as axisymmetry, continuity, and homogeneity, because we don't have in general information about uh, the lack of axisymmetry in some pavement or lack of discontinuities or inhomogeneity. Uh, I also assumed so I didn't simplify the assumption with respect to the dynamic nature of the problem, and I consider the dynamic effect of the load, and I use the frequency domain to solve the problem, and I use semi-analytical approach, the thin layer modal solution, to avoid the 2D discretization of axisymmetric finite element and reduce the computational costs. Here is the linear elastic wave equation in axisymmetric coordinates. We have three types of derivatives in that, with respect to the radius, with respect to the depth, with respect to the time. And one by one, we want to get rid of them to avoid the discretization if we can. So here we take the Fourier transform on time, and then it becomes a multiplication, this derivative, and here it is the Fourier transform of that equation. Then we want to get rid of this derivative based on radius, and we take the Hankel transform. Hankel transform is also the same as Fourier transform in 2D, and it discretizes into Hankel, first Hankel and second function, second Hankel function, and here is the form that we see. Then we discretize in depth, and for doing that we use for the elastic layers CFEM, complex length finite element, which reduces the computational complexity, because we want to consider the subgrade as half space. So we use a significantly large depth for subgrade, and if we want to use general finite element, we need to discretize it in many elements, and it increases the computational complexity of the solving the eigenvalue system. So we use the CFEM, which has the exponential convergence. You can see the details of that in my thesis, and also in its original paper written by Gudati, Droskin, Vaziri. So we have the system of equation. We solve for the general solution, and we find the eigenvalues, the radial wave numbers. This case, we solve for case which makes these matrices singular, and then corresponding to that the eigenvectors. And then we will have the modal expansion of that the causal is made this derivation that based on each in the vertical direction based on each frequency, and each distance you can find the vertical deformation. To avoid solving this eigenvalue problem for every and each frequency that we want to every and each frequency content of the load, so we use the Padda interpolation. The Padda interpolation is just division of two polynomials, one polynomials over other one, and it avoids the computational complexity, and it is just for making things faster. So instead of 10,000 solving of eigenvalue problem, we just use 40 Padda points, and then using interpolation in between. Then so this is one of the ideas that it was very helpful. Then we can use the inverse Fourier transform and find the response in the time domain that we can compare with the measurements on field. So one of the main advantages of our forward model is that it is robust. For getting any intended level of accuracy, we can do the convergence study on that. It was observed that the maximum frequency of 250 Hz with frequency interval of 0.025 Hz is sufficient to capture the frequency spectrum of response, and using 20 CFEM for 16 meter subgrade can represent the response of half space subgrade for vast majority of the ranges of pavement structures to obtain less than 0.5% relative error. So given the load, we can get the deflections at different distances, as you can see, 0 inch to 48 inch in this case. So for validation of this forward model, the most important part is that if it is valid in the reality. So we consider the NC96 pavement as a distress pavement that we wanted to evaluate, and then we the expert didn't see any didn't observe any visible major cracks on the surface of pavement, and we had 14 core samples we have tested out of 50 that it was taken, and we found the modulus of sublayers by dynamic cone penetration test and also previous data interpolations. All the 14 cases have failed in prediction. For all the 14 cases, the central deflection was significantly more than other predictions. So these two curves, the dotted lines, are our prediction, our forward model response, and these continuous lines are the field response that we recorded. And as you can see, one of the best answers that we got is in the left hand side, and one of the worst cases was in the right hand side. I can say that it was the best one, the left hand side. So as you can see, it is completely different, and even 100% error we have sometimes. So, and the central deflection, most importantly, the central deflection always, for all these 14 cases, it was less than the experiment. Why? At least one assumption in our forward model was invalid. So I make a hypothesis, and then I prove this hypothesis that as I explained. So this is my hypothesis. The main reason for mismatch of the forward model is the prevalence of hidden cracks or debondings, the variation of thickness of AC layer within the range of FWD, or anisotropy of asphalt layer. Pay attention to this or. So one of these is at least true and significantly affects our data. So first I explain the observation, what we observed through the field. Then I excuse me. I explain the mismatch based on this observation, and then I refute the other likely possibilities. This is how I prove the hypothesis. So we observed that 8 cases of debondings, major horizontal or vertical cracks, and striping among 50 taken core samples, that we could not put it under the dynamic modulus test machine. And then here for the schema of that, you can see that we have that major hidden cracks or places of debondings. I show it somehow with green lines, and we have the schematic size of a 6-inch diameter core as these black circles, and FWD loading area as this blue circle, which it is a 12-inch diameter, and we have also area of 50 cores, that is the purple circle, and the radial distance of 60-inch for which is the last sensor of the FWD, to see that what is the range of FWD is the red circle. So as you can see, within the area of 50 cores, how prevalent we have the cracks, that 8 cores can capture those cracks, those major cracks under the pavement, hidden cracks. And here this table is the history of this pavement, that it had 4 times rehabilitation through its history. And the last time it was 2006. The first time it was constructed in 1941. So the second observation was variation of thickness of the core samples from 18 centimeter to 27 centimeter for structure 1 along the 2 kilometer of NC96. And the third observation was that when we tested the cores, one of the cores in the vertical direction, then we took some horizontal cores out of that. Then we saw that the horizontal cores, the modulus of those were significantly less than the vertical modulus of core. So we can say that and because the nature of the problem is bending, and in bending horizontal modulus is more essential in a stiffness of a structure, so it is a very important observation that leads us to say that we cannot rely on the assumption of isotropy. So we want to explain the data that the mismatch by these by these hypotheses, and we explain it only by two things. It might be able we can also explain it by the other things, but just explanation of that with one of these in the hypothesis is enough to say that it explains the observation. So any discontinuity reduces our stiffness, so increasing our deflection. If we have cracks in our pavement, but we assume it as continuous, so it becomes, we assume it as a stiffer structure, and then the deflections that we find is less than deflections that we get in reality. Also, if we have some cracks that that is in tension, because it does not let that energy to transfer to the further sensors. So for example, in this case you see between 12-inch and 18-inch, for 18-inch suddenly we had the drop of the deflections, and it seems that the energy did not reach that sensors, and afterward also. So we can say that these cracks are avoiding the flow of energy, and because of that we face this phenomena. And also for the other case, we see between the 24-inch and 36-inch there was also suddenly a jump in the deflections, and the energy did not transfer. So and remember that this is just a plane, so it is a axisymmetric domain, and these cracks and debondings can be inside the plane or outside of that, so anywhere it can be. And these cracks, by the way, are very tiny that they could not observe it on the surface. So we want to refuse the other likely possibilities. Let's say that we had inaccuracy in approximation of the input parameters. So we want to make the input parameters such that if we made a mistake in those, then we can match the field data, field response to them to our prediction. So we just in our case we want to just consider the central deflection, and we want to increase the central deflection such that it matches the deflections that we measure on the field. The prediction matches the field measurements. Obviously the density is just an inertia, and it just expands the time history, and this bump that we have will become expanded. So this cannot be the case, and it does not help us to match this maximum central deflection. And Poisson ratio, it has insignificant effect, and base modulus that we find it by the DCP data, if that it was 335. Let's consider that we don't have at all base, and we have just subgrade, and subgrade that we consider as 130 megapascal. Let's say that we use the least modulus for the subgrade in the literature, which is 35 megapascal. So even with all these softenings, and also considering the top temperature 3.17, and we increase it to 4 degrees Celsius, maybe there was an error in the measurements, field measurements. So we just round it up to 4 degrees Celsius, and also because we found the bottom temperature of the asphalt by the Bell-tree equation, and we may have plus or minus 5 degrees Celsius error for that, so we just increase it to 10 degrees Celsius. And we know that if we increase the temperature of the pavement, it softens it. So with all these softenings, we cannot match the maximum deflection with the maximum of the field measurements in the central deflection. And as you see, it was just this reducing the modulus of subgrade was just increasing the deflection wall, and we have still 30% error. So it cannot be the case. The assumption of the linear temperature profile along the depth of AC layer is also cannot be the cause. The significant shift of whole temperature profile could not justify. So its nonlinear gradient cannot either. This Peltier and all those, their curvature is much less than their accuracy. So there is no way that we find even that temperature profile, and it is not significant. Its effect is not matching our data. Here, inaccuracy in the assumption of one AC layer. So this is the one of the most important ones, that if we assume the isotropy, so then the modulus of AC layer in our case is about 30 gigapascal, and it is about 100 times stiffer than its sub layers, supported layers. And we can say, by looking at this curvature, which is a deflection ball, this is a deflection ball, and you can consider it as axial symmetry. So it's like a deflection of a plate that when we load it, then this is the deflection. So we can consider that as a bending of the plate on the elastic foundation, and because it is 100 times stiffer, this plate, so we can consider it as a bending of a stiff composite plate, which is including several asphalt layers on the very soft elastic foundation. We want to now show that it is only sensitive to change of the composite plate modulus, not modulus of individual AC layers. Means that if we have the equivalent modulus of the AC layers something, then if we change that composite modulus, then we face the different we see the sensitivity. But if we go along the same composite modulus, then we don't see the sensitivity, and this is the space of non-unique answers that we faced when we were trying to do the back calculation. Here I can show you one example, as I mentioned in the appendix of the chapter 2, that we have this red AC layer, and if we decrease its space by minus 21.5%, and then we consider this dotted line above, and we increase it about 30%, the modulus of pavement, then the composite modulus of those, if we apply the FWD road on that, we see that the deflections are not in any point different more than 0.5 micrometer than the response of that red AC layer, that red pavement. So as you can see, and also this is a continuous space. So between these dotted lines, we have all these pavements, that is a ratio of between these can be also our answers. So we have a infinity answers, and this is a space that we can say that it is covering all the possible range of pavements. And this 0.5 micrometer, by the way, is very small. As you can see in the right hand side figure, these dotted lines and this red line is almost, it is matching, and you cannot differentiate it by eyes. It is very hard to differentiate it. It is not also for the sensor locations that we have. For all the sensor locations, it is almost for all of them, it is less than 0.5 micrometers. So if we change even the position of the sensors, we don't get better answers, and we have this problem of non-unique answers. This 0.5 micrometer is more accurate than even the laser sensors, that in the lab condition, if they can do the test. I saw in the literature even we have 25 micrometer inaccuracy in the data of the FWD. So it is about 50 times more accuracy even we faced then after that non-uniqueness. So we use these to prove that with the assumption of isotropy, the assumption of one composite AC layer was reasonable in our case. So if we use one composite instead of several AC layers, if we have the isotropy, if we use several AC layers, or we use just one composite layer, it doesn't change much. And remember this 1.3% relative misfit that and compare it with 4% that I mentioned in the last slide also. What about the inaccuracy in the approximation of phase angle? I saw that the phase angle does not change much because we had an impulse, and this is not the case for us, and it is not changing more than 1%, the different approximations of that. What about the inaccuracy in the extrapolation of sigmoidal function? The frequency content of the response in the time history is not has not that much share that we see the differences of that extrapolation. It is also less than, it is causing less than 1% error, less than 1.5% error in our deflection. So this cannot be also the case. Error in the measurements of the field response, as we know that they do the regular calibration based on the maximum deflection for FWD. So maximum deflection is completely mismatched, so it cannot be also the case. Inaccuracy in assumption of half space, if we just bring the half space close, if we just make the stiff layer closer to the surface, it will just increase the stiffness of the system. So obviously it is not increasing our deflection that we can match with the measurements. The prediction matches the measurements. And inhomogeneity within the mixture of the AC layer, because the different sizes of aggregates are not comparable to the size of our experimental setup, so this is a good assumption that we consider homogeneity. And also there was no accidental error. All these were all the 14 cases has failed, and the 2 consecutive drops were also giving us the same deflection, so it cannot be the case that it was some accidental error during the experiment was happening. And did I miss any other significant assumptions? So I appreciate if you bring any other thing that if I missed, but these are the likely possibilities that reached my mind, and I refuted those. So with those being said, the hypothesis is proved. So it can be said that these reasons will affect the FWD response significantly. Is it feasible for us to model the hidden cracks or debondings and their relative location with respect to the center of the load? Is it feasible? Is it feasible to model the variation of the thickness of AC layer within the range of FWD? Or is it feasible to model the anisotropy of asphalt concrete layer? Since we have no information in general about these complexities from the field, the prediction of response or making forward model is infeasible. Hence, back calculation due to the use of forward model is not feasible also. It's a beginning step, so it has no sense that we go through the back calculation. Also, there is no feasible method to gather the database for doing artificial neural network considering the effects of these complexities. The artificial neural network is a large database that if we consider all the possibilities that can affect our deflections, and then we gather the information and properties of those pavements, and we make a large database that it covers all the possibilities. Then if we find the response of our pavement close to one of those possibilities, then we can prove that there is no non-unique answer, so we can say that we found the properties. So this is a way to avoid the forward model by computer. But since we don't have this database and it is not feasible method to gather this database for doing artificial neural network considering the effects of these complexities, the cracks can be at any location, at any position, and it is hard to first gather and also to know where is the cracks exactly, and know what is the condition of that pavement. So this is not feasible also, and there is no warrant that we do not face the problem of non-uniqueness for artificial neural network considering the range of errors of field measurements. Hence, for this pavement, FWD by calculation is not feasible. Almost every to answer the question that we had initially in our lecture, can we translate these pointwise deflection into some other quantities such as modulus of asphalt layer, which can be used for pavement evaluation? No. This is only 2 kilometer of 180 kilometer NC96. So obviously neither of these single points can be considered as representative of the length of the pavement, and we cannot design the overlay or qualify the pavement by looking at any single point of these curves. So there was an idea that instead of doing by calculation, directly we use these reflections in some way. Let's say, for example, the elastic back calculation, and then we design the overlay for that. But the thing is, which one we want to design? Do we want to design based on the 0.4949, or we want to design based on 0.1159? If we design for 0.1159, it might not be effective for 0.4949, and if we design for 0.4949, it might be not be efficient for 0.1159. We want to design for the length of the project, the length of the pavement. So what if the design programs are giving us almost the same answers given any of these pointwise FWD responses? So maybe, for example, some design program says that even though that I have high variation, I just give you the answer that is efficient and effective for all these. So it means that, and by the way, all the programs, they are using only single FWD data currently. It means that they follow a procedure which is independent of FWD test, and FWD test is at its best redundant. This is also the case for the expert engineers who require taking FWD before they design due to their judgments. Engineering is only defined within the borders of true science. We cannot claim something as engineering which is not scientific. Someone may offer that we evaluate pavement by sufficiently large number of these pointwise data. Can we? We use again our proved statement of hypothesis. FWD response is highly sensitive to prevalence of hidden cracks or debondings, significant variation of the thickness of AC layers within the range of FWD, or anisotropy of asphalt layer. Cracks or debondings are always increasing the deflection under the load. So obviously any type of averaging techniques will not eliminate the effect of them. If the cracks increase, so the average is also increased. It is not a random uniform distribution or normalized distribution that it cancel out each other, these errors. So this is why that we need scientists that they decide. Also, we witnessed a high variation of the AC layer thickness along the pavement. So this is along the pavement. Pay attention that we witnessed that along the pavement we had variation between the 18 centimeter to 27 centimeter, and the course that it was observed from the course that we took. But in our hypothesis, it was within the range of FWD. So in general, AC layer is significantly stiffer than its supported layers, and the variation of thickness of AC layer has significant effect in its stiffness of pavement, and so its response. And core modulus proves that we cannot have a generalized anisotropy along the pavement. All the core properties, it was different, so if we don't have a generalized, we cannot generalize the modulus along the pavement. We have no information about any of these complexities to eliminate their effects by any generalized function. So coming back to the question that whether we can evaluate pavement by sufficiently large number of these data, we ask, is there at all any quality representing the condition of pavement in these data that we quantify it for pavement evaluation? So if there should be some quality that we quantify it. If there is no quality, how we want to quantify it? For example, if we can say that at the point 0.4949 millimeter shown in the picture we had low quality, and at point 1159 millimeter we had good quality, can we say that? Can we say that at this point we had good low quality, and at the other point we had good quality? At point 1159 millimeter we could have thicker pavement, and does having thicker pavement mean well conditioned pavement? Or for 0.4949 millimeter we might have prevalence of hidden cracks and debondings. Does it disqualify the AC layer at its surface? Here I took this picture just Avon Ferry Road, in front of the Burger King. There is a just asphalt, new asphalt, which is on top of a very distressed pavement, and this does not disqualify. When we have the hidden cracks or the bondings under the pavement, it doesn't disqualify pavement on its surface. So the answer to all these questions is no. There is no quality. And we can conclude that FWD test has failed for mentioned sections of NC 96 evaluation. Definitely it was failed. Can we generalize the that FWD fails for all pavements? No. Right now in my thesis I don't claim that, but yes, I also, if people were trying to understand, then I was also able to prove based on my program that even the idealized pavement, because of the non-unique answer and the lack of accuracy in the measurements and known and the given parameters, we cannot also do the uh, back calculation even on the idealized pavement. But now I just consider no. We don't conclude right now, and we don't need to conclude, and we see that why. What we refuse is reliability of FWD. Without any proof, FWD companies are uh, charging taxpayers for their claimed experiment. We found that it is not working. For an example, we proved by rejecting the general statement that it is a reliable test, that it is widely used. So, by a contradictory example. So, we have the right to say it is not reliable in general statement before they can prove that what are the limits of the application of their proposed method. The burden of proof is not on the taxpayers. It is on the one who proposes a method for the problems. I witnessed many contradictory and false claims in the literature that makes me hard to believe that the companies are not aware of unreliability of their methods. Since it is beyond the scope of my PhD and I'm not a public attorney, I did not criticize their papers and reports, but this is also a necessity for the society. I am not the criminal one to pay the price of the others' false claims. By other hypotheses, by our hypothesis, we proved that the FWD response is highly sensitive to prevalence of hidden cracks or debondings, variation of thickness of AC layer within the range of pavement, or anisotropy. And FWD is only for evaluation of distressed pavement properties. I remember that I asked for new pavement data, some bridging pavement data, and the one who was responsible for that told me um, that you will not win this battle, and we don't do the FWD test on the new pavements. So the context of reality is that if we can assume that it is not distressed, why do we evaluate it? So we always do the evaluation on pavements that is distressed. For general distress pavement structure that we are tending to evaluate it, there is no warrant that we do not have prevalence of hidden cracks and debondings under its surface. So we cannot rely on the assumption that we don't have prevalence of hidden cracks and debondings. So we cannot rely on FWD. For general distress pavement, there is no warrant in current construction methods that the thickness of AC layer does not vary significantly within the range of FWD, like if it was the case for NC96. So uh, there is no warrant, and we cannot rely on this assumption that we have a we don't have variability of the thickness along the pavement. And pay attention to these ands, these or and ands. And there is no also reliability, there is no warrant that we do not face anisotropy like what we observed in NC 96. So we can not rely on the assumptions of continuity and axisymmetry to do back calculation. And since these complexities vary along the pavement and we have no information to eliminate their effects on deflections, in general we can conclude that FWD is not reliable for pavement evaluation. This statement is 100% true in reality. It is not 80%, it is not 20%, it is 100% true in reality for current pavements, and it is independent of the choice of NC 96. If we were living in the other worlds, any true statement in this world can be under question, but we are not. So, for example, let's say in a dream, your dreams, you may fly and there might not be any gravity. So, if someone denies the context of reality and follows irrelevant assumptions of his mental ideal world, he or she is not a live human in this world. How can I communicate with such moving object? In the literature, I see that they say the elastic models work. Something that you cannot even validate it when we all know that pavements are viscoelastic in reality. So they assume something that all these years they were assuming something, and they made programs for that you cannot validate it. You cannot see if it gives you something true. And then they say that it works. So if they assume that it is working, it is the end of science and discussion. If you assume something is true, there is no discussion on that. So summary, can we do back calculation for this pavement? No. Can we rely on any single of these data points for our design or decision making for this pavement? No. Is it essential for trustworthy design programs to or experts to have FWD data for this pavement? No, it is redundant. Does obtaining many FWDs along the pavement help? No. Can we qualify this pavement with FWD data? No. Can we rely on FWD for evaluation of the other related pavements? No. Is it making life easier and better for the society to continue FWD tests? No. They ask what is the alternative if you say that we do not take FWD test. This question does not justify to continue unreliable methods. First, pavement engineers must reach conclusion about what parameters they need to know from reality, and then they must decide about designing and applying reliable methods. What about the number of jobs that will be lost? They say that, you want to take our jobs. So, job is only justified when there is a need. Yes, there is a need for maintenance, and maintenance, I mentioned that it is very necessary. But it does not mean that we should make some nonsense experiments to find out what. So nowadays the governments, all the jobs, if there is no need, actually it is a burden. It is not a good thing. Nowadays, the governments all around the world are keeping their nation in need and busy with nonsense jobs. This man-made unjust slavery has to change. Someone may say that these assumptions that you refuse, such as continuity, isotropy, and axisymmetry, are the accepted assumptions for many pavement programs, and pavement researchers have accepted them as accurate assumptions. I do not claim that all the programs which consider pavement with those assumptions are not reliable. However, the researchers must search for clarification of the truth in reality. They must not search credits, for example, writing papers, publishing papers, by falsifying the interpretation of the real condition due to their unrealistic assumptions. Yeah, this is also the cause of another, the effect of another cause that, yeah. Until now, so I proved the main claim and title of my thesis. How can I just eliminate the most beneficial part for the society? So what is the point of doing research in the university if I just eliminate the main beneficial part of my research and I just show some forward model, something that is we do it in the computer fast, So the rest of my presentation is only for fulfillment of the requirements of my PhD and its publication. It is about idealized viscoelastic layered media for the ranges of properties and geometries of pavement under virtual load, and it does not have any immediate use in reality. The researchers on the other fields may benefit some of these intuitions and observations for their field. I did the back calculation by using a hybrid method of Gauss-Newton algorithm and Monte-Carlo algorithm, and you can see the formulation. This is the misfit, which is the difference between the synthetic data and also computed response, and we find the derivative of that based on each parameter as a gradient and also Hessian matrix that we simplify it to positive definite, and we use the Gauss-Newton algorithm, the step size of that, and then we use for getting the derivative we use the finite difference, and we used it because it was cheaper than the other two methods, and also the analytical derivative you can compare. You can see in the appendix of chapter 4, and it might be helpful the derivation of that for the other researchers. We use the time limit because we had a truncation in the response, and we use the truncated power law for approximation of the viscoelasticity. We could not find more parameters, sensitive parameters, and we use just only two parameters, which is the E star at 5 Hz and E star at 40 Hz. We saw that it does not vary for a variety of sigmoidal functions if we consider the sigmoidal function and all its parameters, and we just use this truncated power law. The response, the prediction that we have, the synthetic data, does not vary more than 2%, and 2% is pretty much better than the accuracy that we have from the field measurements. I see that in the literature they say that we find for you even the thicknesses, we find for you the time temperature shift factors, we find for you all the 4 parameters of the sigmoidal function. Whatever you ask, we give you. They should not do that. This is not honesty. So we don't have sensitivity that we claim about things that, and also about the phase angle. I use the slope of that, this slope of these curves. So we have eventually only 4 parameters. One is the modulus of the pavement, modulus of the AC layer at 5 Hz, modulus the norm of the modulus of AC layer in 40 Hz, and modulus of the base, elastic modulus of base, and elastic modulus of subgrade. I saw that if I change the parameterization into 1 over these quantities, then it makes my objective function more smooth, and to avoid the jumps that we have in the resonance frequency. So it was one of the ideas that the other researchers may benefit from my experience. These are the boundaries that I explained in my thesis, that we don't let it do this is the constraints that we have. The back calculation that we do is the under the constraints, and these are the constraints. You can find it in my thesis, and so basically the goal is to minimize this misfit, which is the relative misfit, and the criteria, for example, to stop can be 0.1%. We use this very low to say that even our back calculation is robust for vast majority of the cases, and we used also 5,000 evaluation of the forward model as a stopping criteria that it does not run forever. So so we begin, and also the Monte Carlo region that you can find it in my thesis, the details of that. So we initiate with an initial guess, and then we go through the procedure of Gauss-Newton, 10 Gauss-Newtons, and if we couldn't find the less than the misfit, then we go through the Monte Carlo algorithm, and then we if within the 250 we found another answer which was had less misfit, so we again go to the Monte Carlo. But if we couldn't, so we add 1 to the counter, and then we go to the Gauss-Newton algorithm, and we less than we don't let it to be more than 5 times this loop, and if we couldn't find the required misfit, so it goes to and uses another new initial guess. And this procedure is not, as I mentioned, we don't let it to go beyond 5,000 function evaluation for what method evaluation. So I saw that we can find what is our what should be our misfit for different systems, and we can study that. As you can see, it is like a line that we see in the right hand side figure, that if we have 0.1% error in misfit, then we face less than 2% maximum error in all the parameters. So for this level of accuracy, we need this misfit, and you can find for the other levels of accuracy also. It's like a line. But problem to problem, it is different. And in this case, we found in 1,300 evaluation of forward model the answers. So I did for one viscoelastic layer, but my program has also the option for doing back calculation on multi-axis layer, and also, but I do not warrant anything about that. And it uses the deterministic known parameters such as depths, Poisson ratios, densities, time temperature, shift factors, temperatures, and it considers also the different ranges of the temperatures from -10 degrees Celsius to 70 degrees Celsius. Uh, and we could, for considering that 0.5% relative error, and as you can see, it is very close that you cannot see by the eyes the difference between this black line and red line. So for 0.5% error, relative error tolerance, less than 10% error we got in vast majority of the cases for our parameters, and it took less than 15 minutes. In average, it was less than 8 minutes. Uh, I should also mention that for more than 4% misfit, I observed that extremely large space of non-uniqueness for all the cases, even synthetic data with no noise due to the large relative errors of approximating input parameters, and lack of any claim on the accuracy of FWD measurements. So because we face these large relative errors in the input parameters, and also we have the inaccuracy of the measurements in the FWD, which is more than even 10% error, and with 4% error, I saw that it is covering all the ranges of payments, and even beyond that, we don't get at all anything that is that makes sense. So this is not even for it is not also feasible for to do the back calculation for even idealized pavement. Thus, even for idealized pavement, back calculation is not feasible. I made my argument in the appendix of second chapter, but since the professors do not believe in my experience on the code that we developed together when it comes to publication, I just mention it as an experience in the appendix. It's interesting that people, they believe in the experiments on the laboratory, but if I do the experiments and I witness the experiments results on my code, they don't believe in me. I just so the challenge is that for them is that they give me the properties of their chosen pavement, and within the 4% relative error of its response, I give them the space of non-unique answers covering all the ranges of pavements, as we have done it for that pavement, that's pavement 1 and pavement 2, that we had explained in the proof of our hypothesis. So any expert cannot claim that FWD back calculation on even idealized pavement gives him intuition for design, because it covers all the ranges of pavements can be the answers. For simplicity, attached to my thesis is the codes to testify my claims for readers. The only witness and judge is the truth. I express also my gratitude to my previous advisor, Dr. Murthy Gudati, for his thoughtful instructions for theoretical models of my research. I do also appreciate my friend Ji Zheng, who has done all the testing all the core samples as a PhD student at NC State, and also Dr. Konjing Lee, who have fulfilled the experimental part of the project in coordination with the NCDOT, North Carolina Department of Transportation. And thanks for watching. And if you, I appreciate if you send your questions to me, and feel free to, don't hesitate to contact me with msahafi@ncsu.edu. Peace be on you all.